Okay, so here is the second attempt at office hours for AMATH 352. It's October 31st. Okay, so someone asked a question about whether, basically what the fixed point of it's 1.3?
1.24 on question like 10, 11, 12.
Okay, so
14, 15.
The quiz question's asking what are the behavior of these different g of x formulations.
And h of one, h of x.
Yes, and yeah, the different h of x and g of x. Okay, so for, I don't remember the problem number on the homework. What was it?
Question 10.
Question
On the
10.
Homework?
Yeah, because these are all based on
Yes.
Problem 1.38.
right. Okay, so for 1.3, there's this function. What was the f of x equals 0? Do you remember? I don't. Should I pull up the function, or can you?
Yeah, we can. Okay. So
I mean, is that graph just something on the rhythm part? That's not.
So I think the confusion is you take this function. There's A, B, C, D, whatever.
Yeah,
A, B, C, D.
And these are each a g of x that satisfy. Like these are just rearrangements of each other, right? So you've got A through E different rearrangements of the same equation. So if P satisfies f of x equals 0, it has to satisfy g of p equals p, which, if you remember, the definition of a fixed point was that if you plug it in, and same thing in and out, right? In equals out.
Yeah, but like some reason it's not the fixed point because like it diverges.
So right, so these are the different things. There's one is does the fixed point exist at all? Right?
Yeah.
So is there a number you could plug in and get in equals out? So that's one question. But then this next question is, can which very generally speaking, algorithm could mean a bunch of things, but in this case, it's this g of x, right? Can my algorithm find the fixed point p? Which this is the question of convergence versus divergence. So even if the fixed point exists, it may not converge to it. That doesn't mean that if you took the actual answer and plugged it into that g of x, that it wouldn't solve that it wouldn't be a fixed point, that input wouldn't equal output. But that still could be true. But then when you do the iteration, it might diverge or it might do something else. So
okay.
Does that make sense?
So if the function diverges, we can still find a fixed point.
Yeah. So even if the function diverges, it still may like plugging in the fixed point may still solve the equation.
Oh, okay.
But that doesn't. But it's not an effective method of writing an algorithm to find it.
Yeah,
right?
but how can we find a fixed point from the graph we plot?
Right, okay, so you're making a couple different types of plots, but the main one is you have iteration number and then the value
the relative value
x or equals, let's call it pi. Or what was I using? Was I using k for most of these? K minus 1. So what the iteration value is, right? So sorry, this would be k, what iteration we're at, and this would be the value that you get out of g at that iteration. Okay.
So
So on the first one, it's going to be whatever you've done.
So
How the
1.1
numbering works.
1.3 is something like this.
Right. So
So like,
yeah. So you should if you put in a guess, and then you plug that guess in, right, and it goes to somewhere else, and you plug that in again, and it goes to somewhere else. The question is, what is it doing in the long term, right? So is it getting closer and closer to you, which would be converging to that value?
Yeah.
Or is it getting, like, it could be doing this in a variety of ways, but is it getting larger and larger, which would be going away from the value? So this is, the geometric thing of, if you have something that looks like this, and this is your first guess, so that's that may be the second guess. That would be the third guess. So if I plot what those values are, that can be jumping around, but the question is just, what does it do as it goes further and further in? So does the relationship between this and that plot make sense?
What's the name for this guy? This one?
So this is just literally my function g of x, and then
Y equals to x.
Okay. Yeah. Sorry, y equals g of x. So this is just a plot of my function again, and then a plot of the line of x. So I would call this the graphical solution of g of x equals x.
Okay.
So you don't have to plot this, but it might be.
But you gave us the code for that one.
I did give you the code for that. So because it's always useful, like if you want to figure out what's going on, one of the best things you can do is just look at what's happening, look at your function.
Yeah, but I have a question. Like, so if for the 1.3a, so we can find the graph like this. So we can tell it's converged to some points.
Yeah.
But for the 1.4a, it's like it drops to the.
It's
Well,
actually
look at-
diverged, right?
Yeah, look at your y-axis. Look at the value.
Yeah,
on the
it's very
y.
large.
It's very large.
Yeah.
And if you plotted this on log, you could actually see how it would chop all of the ones that were negative off, but you could see all the values that were positive iterations. So he's looking at a plot that has like a 10 to the 306 or something like that.
216.
216, all right, whatever. 216, which I don't know if you remember, but what do you remember around
That's
the
the
range of
largest,
the biggest
yeah.
number that you can get? Do you remember?
Around that number.
It was
Something
it's,
around that.
it's somewhere around here. So this is like the largest number that MATLAB can even handle.
Okay.
And you see something that looks like this, which is actually, this is just one data point and then a bunch of data points
There are a total like
that are
seven.
all so
seven,
small.
Yeah.
that you can't, like, they're all so close together on this scale, you can't see them, which is why I would suggest if you plot instead. So again, this would be iteration number versus PK. So really, it's not like you have a line of values here. It's actually just jumping from one value to the next. So
At first, we thought that seventh point was the outlier, but I don't, just because the eighth point, MATLAB just say n in the end. Yeah.
Yeah. So why do you think it's showing you?
Being like larger.
average the maximum that we put in 10 to the negative 6.
So no,
But the number we
so-
collect
not
smaller
negative.
than that.
so it's not converging. So if you were below the
Diverging.
tolerance, right,
Mhm.
Yeah.
it would stop. But so what do you think?
I think
So
there's
you will stop, but it's still not converge, it's still diverge.
Right,
Because
your algorithm can stop, but still not.
I think data just explode.
Yeah, so this would be, I would agree. I would call this the exploding.
Okay.
I think this is fair to call this exploding. And so the reason it gives you not a number is because it actually, the next time it tried to call the algorithm, MATLAB tried to return a number that is larger than a number MATLAB can store.
Mhm.
So it actually stopped because, I mean, I don't know if it's, did it go out to 100? No, it only went out to 7. So I think
Yeah.
it stopped because it hit not a number,
Mhm.
and like then that caused the loop to just stop because they, you know, if it tried to plug not a number into the next thing, I'd have to go and look at exactly what the code is doing to know why it stopped when it got not a number as the iteration value.
Yeah, but how do we comment on this kind of question? So we just say the number goes too large, so we
And just
can
say
ask the
explode.
conclusion for that.
Well, so is it converging?
No, it's
No.
not.
So is it diverging?
Yes.
Yeah.
Uh-huh.
So this is the kind of comment
Oh,
that I want you
okay.
to make is like,
Okay.
what is the behavior?
Yeah, but like I have added something like we cannot find a fixed point for that. So is that kind of true or false? Find a fixed point for all
For
the kind of
divergence, yeah.
functions.
That's
So-
not gonna be a reason, right?
If you take the fixed point you're getting as the solution from the other algorithms and plug it into that g of x that caused the divergence, it's not it's not the fixed point doesn't exist, but
Oh.
it is the algorithm can't find it because that algorithm
Okay.
diverges.
So I should say the algorithm kind of find it, but I should not say the fixed point is not existing.
Exactly.
Okay,
You shouldn't
cool.
say exactly. Yeah, because the only thing that tells whether the fixed point exists or not is whether or not there is a solution.
Oh, I
Right.
see.
And since they're all the same equation,
Mhm.
they should all have the same solution.
Oh,
Okay.
gotcha. Okay.
Okay, and just like according, I just checked my answer. I feel like for those that converges, it converges 1.124.
Yeah, so it looks like the quiz might have the wrong fixed point value
Mhm.
on the quiz. So
Well,
yeah, so they should all be the same. Is
Yeah,
like the point we've come to. But yeah,
Yeah.
you should ignore like the value doesn't actually matter for the
Okay.
for the solutions.
Okay.
Sorry about that. That's a typo.
Cool.
Cool. I
Do we
also
have-
have a question for like number 2 is actually asking for the
Can you just explain us what it? Yeah.
Is it the same question?
Yeah, same question.
Okay.
Can you just explain us what's the questions about?
Sure.
Yeah.
So so it's saying we have a set of 10 vectors and they each have 10 non-zero components. So you can imagine those each as a column vector. And 2 on the quiz.
Yeah.
Do you guys want to take a photo of any of this or?
I didn't bring my phone, so.
Oh, okay. Before I race. Okay. Okay, so the question says, let's say that I have a set of vectors. I don't know, what's the 10th letter? Is it either?
A10.
Okay, what's that?
B10, B1, B10.
So there's a set of these guys and there's 10 in the set, right? That's what it's asking.
Mhm.
And none of the components are equal to 0.
Yeah.
So no A value. So it's asking, I'm saying and you have no additional information.
Okay.
I'm asking, what is the largest dimension that the set S can span? So remember, you can think about,
So if we do RREF, like what value you give us?
so REF on this,
Mhm.
right? If you said, like, let's put this all into a big matrix, and the point of doing RREF to look for what the span of a set of
Yeah.
vectors is that you then look,
N-time and identity matrix do we have?
right,
But I just wonder the definition of the dimensional one span. I mean,
So-
we know like 2 is like 2 times 2 identity matrix, but how about 1 and 0?
so one would be if you only had
1.
one vector that has one
Oh, okay.
value.
But
Okay,
can-
but
it can be
it's
one.
possible. It's possible.
It's
If we
it
have
can be
a
one,
one vector,
right?
that's one. But how about like 0?
So
There's no vector that's one. Is that 0 dimension?
Like,
well, so what if you had,
mhm.
let's do a smaller case. So let's say we're looking at sets of vectors that have 3 components. So what if I had this set of vectors with 3
Is that
components?
dimensional 1?
Yeah, so because these two guys are both like, how could I get to this one from that one? Just multiply by 2 or add 1.
Yeah.
And here I could do the same thing. I could either add 3 of these guys together or multiply by 3, right?
But it cannot be 0, right? Because 0 is just nothing.
Well, I specifically state that none of the components are 0
Yeah.
But
to
I
avoid
mean,
this issue.
I mean, yeah. Okay, yeah.
Yeah.
So it's more.
There is an issue when you allow 0 vectors that comes up, and so I specifically said non-zero. So does that make sense?
Yeah.
Yeah.
Great.
Okay. I mean, I have more questions, but I just feel bad to ask questions
All
constantly.
right, let's wait 15 seconds and see if does anyone else have questions or want me to look at code?
I have a question. Did you adjust the fourth equation of 1.4
I have.
equation?
Yeah, I changed.
H4.
Yeah, so it was originally something like I don't remember exactly what it was, but it was something like this, maybe, and it was missing the 1/2, so I changed.
Okay.
I think that I have that edit on the problem set
Oh, yeah.
page on the website, yeah.
And
So if you had checked, like, is the solution equal, like, is that equation the same as the f of x equation? It wasn't without the 1/2, and it is with, I don't actually remember if this was the right equation, but without the 1/2, it was not the right equation, and with the 1/2,
Okay.
it was the same as that. Does that make sense?
And I think you have mentioned that, but for H1, I got an AN at the end of the vector.
For some of them.
Yeah.
Yes.
So is it correct? This is
So-
what should happen, or should I do something?
So remember when we were talking about machine numbers in MATLAB? Only store numbers,
Yeah.
the computer can only store numbers up to some size.
Yeah.
So if it tries to get to go to a number that's larger than the largest number it can store, it's going to put in not a number. Like, that's the way that it outputs. If you try to access a number that's larger than what MATLAB can store.
So should I stop it before it gets like too large? Or it's okay, just put it.
You should keep the not a number in there.
Okay.
Yeah,
Alright.
I think that's important when you're calculating the error.
But for the error, I also got the NaN.
Yeah, I'm saying, I think that when I uploaded the answer key,
Okay.
like, I didn't do anything special with the not a number, so you want to keep it in there.
Alright.
Yeah, I have a question. So, for the question number 5 on the quiz, so there are 3 column vectors here. So, but I don't know what does it mean by like add one column vector to the set of vector to form the.
So we try to do we try to concatenate all those options with the matrix and then do the rational reduce. I mean the
REF.
the REF, and then it works for everyone.
Everything.
So
Every single one.
Every
so
single one.
every
Yeah.
single one is independent.
Give us a diagonal.
I don't know
Okay,
if
I'll go
it-
double check it. That was the one that it had, like, wasn't that the one that I said there was a correction on?
Oh,
Wait,
wait, what?
Which one?
I think so.
Did you?
No, did I give you the wrong problem number in addition?
Number
It's
5.
number
I
5.
said 5, and then what did the email say?
Oh, let me see.
Yeah, but like if I do the rifting first
There
for
is an
the
error.
It's reduced row echelon form is
Yeah.
what that stands for. Just so that we have a
Yeah,
thing we can say.
yeah,
Okay.
reduced echelon form. Okay, if we do that first for the three column vectors, one and the last row is all zero components. So we so in that way we add the second question second answer to that. But if we concatenate the vector first, we got all the same answers. Yeah.
Well, so it's asking which of the following vectors can be added to form a basis. So you do have to evaluate each potential basis separately. Does that make sense? So you can't, like, from just having, because, all right, if you do the reduce row echelon command on just the three,
Yeah.
and then evaluate what comes out, you're not performing any of the row operations that you performed on any of the test, right? Like, or on any of the answers. So if you, like, you can't just then add that guy in at the end. Like, it might be that for the one that it works for, right, that you look at and you say, oh, if I just add this one onto the one that I have reduced, that all the manipulations you did wouldn't have done anything because all of the manipulations would have been on factors that were zero.
Oh, okay.
But for the rest of them, where it was operating on non-zero stuff, it doesn't matter. Does that make sense?
Oh, okay, cool.
Yeah. Did that make sense?
So what did you?
I think so.
So what did you change to?
There's no change to the way the question's phrased. I just need to make sure that it's graded.
Oh, graded.
Yeah,
Okay.
yeah.
Oh, so you change the points? with
I
the-
have to change the
Okay.
points on my end, but the question doesn't change at
So
all.
if we submit it, it might give us like wrong.
It might tell you you're wrong even though
But
you're
we-
right. So
okay.
just, yeah,
Or just ignore the grade.
or you can wait until I update it before you put it again. And yeah,
Okay.
So here it gives us three column vectors. We have no needs to change them to row vectors. Right? If we try to see if they can form a basis in output.
okay, so the way that we've been thinking about linear independence is in terms of column vectors, right? Because we multiply.
Okay.
But so generally speaking, if you want to know whether a set of column vectors,
Yeah. Okay,
yeah,
Because the C1, C2, it stands for
exactly.
coefficient for the column instead of.
If you wanted to know if row vectors were linearly independent, you could just take the transpose and turn them into column vectors and do the same thing.
Ah,
Okay.
yeah.
So, and generally speaking, a matrix could be linearly dependent in its column vectors and not linearly independent in its row vectors if it's rectangular, right? Like if it's not the same. It's wide as it is tall or tall as it is wide.
Yeah.
Which I think we talked about before. If it's square,
It has to be just.
it has to be, if it's linearly independent in one, it's linearly independent.
Yeah.
Okay, so you were still, there was confusion about what I was saying about that quiz? Okay, so I was saying, so the quiz question is, there's some set of vectors v1, v2, v3, and then there's basically the unit vectors, so 1, 0, 0, 0, 0, 1, 0, 0, all of these guys. So if you take those first three vectors and do reduced row echelon RREF on it in MATLAB, right? What you're doing is you're doing row operations on those three vectors. There might be one of these guys where when you go through and do the row operations on all of those vectors, it wouldn't affect, like let's say, to get these guys to reduce row echelon form, all you had to do was a bunch of manipulation on the top three. That wouldn't affect this guy at all, right? If you add and subtract only these top three entries in this column vector, it doesn't affect anything. So it's possible for you to do a bunch of reduced row echelon operations and have it not impact the result for a particular vector. But if you want to check if if like any of these can be added to make a basis, like it might doing those row operations on the other ones might. Does that make sense? So you can't use reduced row echelon, the ref function, check whether some things are linearly independent without including the vector in there. If that does that make sense? Okay.
Yeah.
Yeah, so I just wonder what is the, I mean, like on, I think like for 5 question, like question 14, 12, 11, 10, it both like say something like the absolute value of the derivative of the iteration, something, I just wonder what is that?
Screen.
Like what I mean by the absolute value
Yeah.
of the derivative of the iteration scheme?
Yeah.
So I mean, we have the iteration scheme is, in this case, our function g.
Yeah.
So the absolute value of the derivative of the iteration scheme is the derivative of g of x absolute value.
Okay.
And it's, you need, like,
We need to find out that it's bigger than 1 or smaller than
How
1.
fast?
Or is there
Oh.
anything associated with its divergence or
right, so this is
Okay.
theorem 3 that we went over.
Yeah.
Do you want to?
No,
You
I
seem
mean,
very excited.
no, I mean, you said like if it's greater than 1, then it diverges. If it's smaller than 1, it converges. But
Yeah.
what I'm curious about the case if it stays at 1, and then that's
Sure.
the case.
It's circling
It does
around the
nothing,
point.
right?
Yeah, so what's gonna happen geometrically if you have, so the easiest, I mean, if it's also 1, then it's kind of hard to see. So let's do derivative -1, which means the absolute value is gonna be equal to 1, right? Or,
Yeah.
yeah, okay.
Mhm.
So here is my y equals x, and here's my y equals g of x, and in this case, it happens to be just -x plus something, so that it's shifted.
Yeah.
Right, all right. So let's say that I pick my guess to be here, right? That's my first guess. I'm gonna go over to find, is that what I wanna do? Sorry. I wanna go,
Find a y value. Y value.
I wanna plug that into my function,
Yeah.
then find the
The
y value. So this is gonna be
The mu x. For sure.
my new, am I doing that? Yeah,
Mu x.
sorry, I always like, when it's not, hold on.
Yeah.
I'm like, because they're now both straight lines, losing track of which one is the,
The one we're looking for.
yeah, so if I plug that in. Right, okay, hold on. Let me start up with my iterating. Okay, so here's my g of p naught, which needs to be equal to my p1.
Yeah.
So I'm gonna go over to where that would be the y value of that. So the x value is gonna be at the intersection. So this is my p1. Now I'm gonna plug that in to my function. Go over to where,
Yeah.
but, so that's the y value, g p1,
And we get the same x again.
and we end up going right back to the same place.
Yeah.
So I can iterate over and over again. P1 equals P3 equals P5, P2, or sorry, P0 equals P2 equals P4, P1 equals P3 equals P5. So all my even iterations are at the starting point, and all my odd iterations are at.
To give us nothing.
Yeah, so it's not, so is it converging? Is it diverging?
No.
No,
So what's
it's
that?
just oscillating.
Hmm.
Yeah. One of the questions in the written parts are very similar to the oscillating ones you were talking about here.
Yeah, so this is a special case of getting oscillation.
Mm-hmm.
You don't necessarily have to have the derivative exactly, like to get oscillation, all you need is that you have for part of the curve, it sends you inward, and for part of the curve, it sends you outward. And if those two things are balanced, the amount that it's sending you inward for the guess and the amount that it's sending you outward for the next guess, you can still get an oscillation even if the if the derivative is not exactly equal to 1.
Well, that's what I meant. Like we have a graph like.
I know you have, yes.
Yeah, and then
So,
is that diverging? Or-
well, is it diverging?
But
Is the error
diverging.
increasing?
we can't really tell from the graph. Like I don't know if it's slightly growing or it looks like it's not growing at all.
Okay, I mean,
Yeah.
that's fair, that's fair. And so really you need to go out to much larger iterations to see. But, so I mean, I will be happy if you just say that, right? Like it's possible,
Okay.
right, that you're saying it's possible it's diverging because I can't tell if the error is increasing or not.
Mm-hmm.
It's also possible it's just oscillating.
Okay.
I mean, one of the things about this numerical stuff is you are only sampling certain parts and you're only going out for some amount of time. You can only analyze what you can see, right? I mean, and that's why we do have all of these theories about convergence or divergence. But in this case, do either of the theorems for theorem 3 apply about the derivative? Like if you look at the derivative, is it strictly greater than 1 or less than 1?
I didn't see that.
Yes, yeah, so that's a thing to check, right? Because the theorem can give us more information than just running the numerical experiment, because it can say, because it's strictly greater than 1, it's definitely going to diverge. Less than 1, it's definitely going to converge. But the question is that one of those cases, or is this a case where you can't say that it's strictly less than 1 or strictly greater than 1 over the entire region it's being sampled? And in class, we talked about like between A and B, so in some region, but in reality, the region is whatever the algorithm ends up sampling.
Mhm.
So,
Yeah, I don't get why the functions diverge when the G prime is greater than 1 or.
yeah, so the easiest, and this is why we're doing fixed point iteration and not a different method, but the easiest way is to look at one of these graphs, look at the graphic representation. So here's a function that has, do we agree that this has a derivative greater than 1?
But what? Okay, so that one's.
Right, because it might just look like S's. Because the slope is greater than the line, right? So
Okay.
this is telling you the derivative of this line is 1. So if the slope of your function is greater than the slope of your line, it's going to be greater than 1.
Okay,
So now if we go and we try to do, like, let me start with a guess that's super close to the fixed point. If I go there and I say, okay, where is that y value? So I go and plug that in. I'm moving away, right?
Mhm.
Like every time I do that,
Okay.
I'm going to move away.
Okay. So
And you could also check that for a slope, the opposite.
okay.
Like still slope greater than 1, but negative slope as opposed to positive.
Okay. So so when we want to find a fixed point for some f of x, so we just first convert to the g of x, and draw the g of x and then y equal to x, and to see if it's to plot the kind of points.
So you can, right, so you can look at it like this to see intuitively, is it going to converge or diverge?
Okay.
To actually do the algorithm, you
Oh,
just
okay.
plug it in, right? Like it's,
Okay.
it's just plugging it in. And you can also, I mean, you should try to look at what are the values of these P's that are being produced, right?
Mhm.
Say, are they getting closer to the value or further away?
Okay.
So how might you design a g of x that you know is going to converge? Because you get to pick g of x.
Yeah, I got it. Yeah.
So, I mean, what characteristic do you want it to have?
Looks simple. Because for the homework, it's like for the first one it works, but for the for the B and C it's not working because it's looks complicated.
I mean, technically, simple versus complicated doesn't necessarily.
Okay.
I mean, I recognize it makes it easier to think about, but what you really, I mean, this is the point, right? Is that if you can design your g of x so that the derivative is strictly less than 1,
Oh yeah.
right?
Mhm.
So
Oh yeah.
then you know you're going to converge. But if you design your g of x so that the derivative, the absolute value of the derivative is greater than 1 within the region of interest.
Okay.
I've given you a bunch of g of x, but in practice, you would actually get to pick.
Oh yeah.
What class are you teaching next quarter?
I don't teach next quarter.
Oh,
Are you doing any research?
I'm just wondering, like any like projected
Um,
teaching for later?
I don't think
So you should.
there's a
convert
chance I
it.
won't actually teach
Derivative
again.
showing.
I'm on the job market.
Are you
So you are looking for professional, industrial job?
No, tenure track. So my job here is
Okay.
temporary.
I see.
Oh, that's.
I'm really appreciating the feedback.
We're appreciate if you make them it easier.
No, yeah, no, I know. Everybody appreciates it. It's easy.
so are you so you're not teaching next quarter? So are you doing any research or like
Yeah, I do research.
You studying research?
Yeah.
what area are you research you're doing?
So, and taking data and for specifically for biological networks. So like metabolism, regulatory networks, that sort of stuff, which is the chemistry that the cell does and the genetics networks of how it controls, you know, happens, right? Like how your genetics control
That's
everything.
pretty cool.
So I take data from that and try to discover what dynamical equations best represent the data using like machine learning. Have you guys heard machine learning?
Yeah.
Yeah, so it's like that except for nonlinear functions, which machine learning is built in a linear framework.
Great.
Yeah, so actually the stuff we're learning right now where you build the function library for the least squares, one of the first things I do is build a function library. I don't use least squares, but and I use a different error metric that
So,
sets most of them equal to 0.
so in order to do those kind of research, do we need to have the backgrounds in biology?
There are lots of people who work on methods for biological problems that don't have a background in biology, but I do. And I found that it makes it, it makes it a lot easier to communicate with the experimentalists.
But I'm just for like students who are interested.
Yeah, no, I would say definitely focus primarily on getting very strong math. But if you have opportunities ever to go, because there's a logic behind how biological systems work that is it's like its own logic, and a lot of it is because it's not inconsistent with mathematical logic. I'm not saying that, but because a lot of biology got built up without the mathematical
By observations.
yeah, by observations. And a lot of that, the way that they do experiments is not, like, it takes a while to wrap your brain around it because it just has been logically built up without the mathematical background. All I'm saying is, like, don't walk into a biology group and say, oh, I know everything about physics, because that won't get you very far.
Wow.
Like, knowing their language and knowing the logic that they have, it is pretty intense in and of itself. So I think respecting that is important.
Yeah.
Are there more questions? I'm happy to stand here and talk about my research.
We just curious.
Yeah, I'm actually really curious about that.
I've also modeled photovoltaics, so solar cells. Generally, I'm interested in very applied problems with messy data and trying to understand complex systems. And basically, what is the easiest way to go from, you have something that has 20 different things that could be going on, and we want to know what are the most important things.
But don't you have to apply some in the area of statistics?
Yeah, so statistics, I'm actually not that great at statistics. I know enough to know, I know the language. I've taken stats classes.
Okay.
I guess that's maybe not fair. Lately, my research has veered more towards statistics because you need the metrics that people use of, is this working or not, right? So but a lot of statistics is developed also with the idea, one of the core ideas is that your data is independent, independently sampled. And for dynamic systems, that's not true. So it's actually I need to know enough about statistics to be able to use some of the stuff they're doing, but also to know when it's going to break down. Okay. And often the stuff I need to use is not traditional stuff you learn in a stats class. It's more dynamics and metrics for that. I mean, I'm several years out of undergrad, so there's a lot of other classes that happen between then and now. I think I took a stats class in undergrad. I must have stats and probability.
But you didn't take much of them.
I took 1 or 2 courses.
Okay. And you were primarily focusing on later on machine learning and stuff.
I would say taking a nonlinear dynamics course and then the scientific computing courses.
Scientific computing.
Yeah. Which have the background you need for machine learning. But my training is not in machine learning. My training is not in machine learning. Yeah, no. My training is I took statistical mechanics. I have a physics background. And then some of the math that's needed. So actually fluids-based math, which is more asymptotic analysis and that sort of thing. But yeah, PDs, ODs, all that stuff.
Are you familiar with dealing with relatively large data sets?
Most of the stuff I work on is not huge data sets. It's more small.
Okay.
Yeah. But if you want to do huge data sets, then you should definitely do the machine learning and scientific computing type classes. I mean, I'd say the difference is I'm really interested in connecting these top-down huge data set type methods with bottom-up modeling where you actually understand the mechanism.
Yeah.
And so my background is in the bottom-up modeling, and I came here because people work on the top-down data-driven stuff. And so we've been working on connecting the two. Yeah. Biological systems. That's what we applied it to.
So they built up the research. They assembled a team just for you should do that?
Well, I work with Nathan Kutz primarily,
Oh, yeah.
yeah, and then I also work with Steve Brunn over in mechanical engineering, and I work at the Institute for Disease Modeling, which is a Gates Foundation funded institute over the summer. So, all right, do you have a question?
For question 13, like they ask me to which one is started when it's not.
I think you're just checking the big N, right? Yeah, how if the big N is big, it's kind of slow,
So,
right?
all right, so let's think about this. All right, so if here, I'm gonna again put my iteration number, or K, here. But now I'm gonna plot my, I don't remember what I told you to plot. I'm gonna do absolute, absolute error,
Mhm.
okay? So let's say that I have one that goes like this. I have another one. This is a separate curve. And then I have
Okay.
another guy that looks like that, right? So first, let's say, which one of these are converging?
Blue one and black one?
If you have
Yeah, so the arrow is going, this is
The both is
zero,
conversion, right?
Yeah, so the blue one and the black one are converging. What's the green one? Because the arrow is just getting bigger and bigger.
Mhm.
And you should also know what
Okay,
this
I
looks
see.
like
Oh.
for the actual iteration values, but for this question of rate, I think it's easiest
Mhm.
to look at the error. So of the two that are converging, the error drops off much faster for this black one than for the blue one.
Mhm.
Now, another consequence of this is because we actually pick an error tolerance to stop at,
Mhm.
right? The one that drops off more slowly is going to take more iterations to get out to the low error
Mhm.
that we want. Whereas the one that drops off quickly may take fewer iterations. Does that make sense?
Yeah.
Yeah. So you can either look at the number of iterations or you can look at the error. And when I talk about convergence rate, it really is coming from how the error going to zero for our convergence system. So what is the rate that the error is dropping to zero?
So when you take the derivative of gx, you have to plug in the value of x in order to get the actual value, right?
Yeah, so you
To
have
see if
to,
it's greater or smaller than one.
Yeah.
But the value changes because the curve is. So
Yes.
how?
so this is why in the theorem, it says it needs to be strictly greater or less than
Always,
for all of the
but
values
do
that are.
you, how do you perform that then? Do you have to? I mean, you can do that on MATLAB and test
Yeah.
every point, but if you do that.
So when you're actually writing an algorithm, you want to design your algorithm so that it is designed to always be strictly
Yeah,
less than.
but I mean, in the quiz questions, do we have to like plot every single
I mean,
point and to see if the derivative is greater or smaller?
you don't,
Or-
you just have to convince yourself which thing is going to be true.
Okay.
I'm suggesting that you can calculate it if you are not convinced of what is happening.
Okay. Fine.
Yeah, no, I know calculating some of those derivatives were messy, but if you wrote a function, there's actually a way you could numerically calculate the derivative, which is you could use the diff command. So if you use the diff of your g of x divided by the diff of x, what that does is it takes the difference between x1, x2, x2, x3, x3, x4, like whatever vector you put in, So this is essentially delta G over, or delta Y over delta X. And it's making a vector of the two. Does that make sense? So it's making a vector of delta Y's, so the difference between each delta Y, a vector of delta X. So it's calculating a discrete derivative.
There's a MATLAB command.
Yeah, diff,
Okay.
just DIFF.
Okay.
So
And what's the difference? Do we need to know, or do we need to set up the difference
So also,
between each X and Y?
if you were calculating dy dx, locally you can approximate it, right?
Yeah.
As delta y delta x,
Mhm.
or y k minus yk minus 1 over
Mhm.
xk minus 1.
Yeah.
So calculate discrete, like it's not that delta y is necessarily useful or delta x is useful, it's the ratio of the two give you the approximate derivative. Yeah. It's taking calculus
Mhm.
from going to the limit of small spacing back to you have discrete spacing, right? If you
Oh,
remember,
yeah, that's right.
yeah.
We have points instead of the.
Yeah.
Like.
So you could also calculate the actual, because you have the function f of g of x. So you could by hand calculate what is the derivative of that, write a function for it,
Mhm.
plug in values. That would be one option. Or you could numerically calculate it because you have discrete points.
Sure.
So when the absolute value is equal to 1, so what's the iteration number versus the iterated value graph gonna look like? So what if it's just equal to 1? It shows nothing, or
I'm gonna erase the
Yeah,
convergence plot.
Yeah.
Okay. So let's do it for this case we drawn up here, right? So for the first, or the 0th iteration, we were at our initial guess. So let's see, our initial guess was maybe -1, and we'll call this 5. So you would have initial guess is here. Second value is there. What is your 2 gonna be?
so it's gonna it's same.
Yeah, so you're gonna go back down to -1, and what's 3?
It's periodic.
So this is what the periodic means, is it's, and if you aren't plotting dots, which by the way, you can change the plot x, y, you can add in single parentheses, O, lowercase o, close parentheses, and it'll plot dots instead of lines. But if you have the lines, it's doing this, right?
But it's not gonna be looks like this, right? This is still not exactly the same. So this is just normal diverge, and that is pure equal to 1.
Well, so this is the question is this actually, so we're looking at the plot for 1.3b, which looks kind of like this, except for it's going between different values.
But it seems like it's just keeping that distance.
Is that what
yeah.
this is doing, is keeping that different distance?
Yeah.
Yeah. I mean, it is technically, you would actually have to go check what is the derivative at both those. So if this was actually diverging, but diverging very, very slowly, what would the derivative here have to be? The absolute value of the derivative at the plugging in this point. So the, no, not on the, sorry. If I take, so if it's diverging, then it has to be g prime of x
Greater than
p naught is the absolute value is greater than 1,
So almost
both
1.
for P naught P1, like it has to be for every single value. So at each of these iteration values, which are just -1 and 5, it would have to be greater than 1 if it's going to be divergent. So you could go and you could check for whatever this the function is that produced this, is the absolute value of the derivatives greater than 1 for both of those values? If it is, then maybe it's very slowly it's very slowly diverging. But if it's not,
I mean, it's still getting a little bigger because at first it's that small, but
well, it doesn't, right? It does at the
it grows a little
beginning.
bit.
But
Oh yeah, the
right,
long
like,
term.
all we
like-
care about is the
yeah.
like whether it's going to converge or diverge.
Okay.
Yeah,
I see.
depends only on the long-term behavior. Makes sense. Okay, yeah.
So actually, I have a question for this one. It says like it all take like 20 iteration to converge. But how can we find which one is faster? Which one is like slow?
看图就可以。
So we were just looking at that. So way to think about it is to look at the error rate. So if you have if you're looking at the iteration number versus for example, I don't remember what error I told you, but PK minus K minus 1. So that would be the absolute error, right? If you had one curve that goes like this, and another curve
So the green one is faster
yeah, because
because the
the
graph.
rate of it going to 0
Okay.
is faster. Yeah.
Oh, so wait.
So when it asks which one has a faster rate of convergence, rate is referring to
The slope?
how the slope of the error
Can
is.
I-
Yeah.
Just draw another graph and.
Sure.
Oops. Not working. Let's see, what if we have something like this? And then we have something like this. Which one converge faster?
So really what you need to know is, so you're saying like it's hard for you to compare what the two slopes are here, basically? Or is that
No,
clear?
I mean, this slope is definitely,
Faster. So it's right, because what happened here, it looks like is you started at a much further away from your actual value, right? So the real,
Oh, I see, you have to start from the same.
you would have to start from the same value to be able to compare the
Yeah.
slopes a little bit better, but the real better way to compare it to a log plot, because if what you're really interested in is the rate on a log plot, that's going to look like one rate and another grade, where what you're now looking at is if this is proportional to some so let's see. Basically, you're saying this looks like k to some power. What is the slope of that power, roughly, right? So the point is a log.
You do log twice. No, log the first.
Yeah, log just means log on both x and y axis. That would allow you to compare the slopes, the power
Yeah.
of the convergence method, which we didn't really get into that a whole lot. But like we didn't do that formally, but that would allow you to compare drastically different initial conditions.
So the blue one converges faster.
Yeah, so the blue one here has because the slope on a log is gonna give you what the power is, right?
Mhm.
Okay, does that make sense?
Yeah.
All right. Okay, I'm going to stop the recording now and switch over to Tommaso here.